Okay. Hey, sorry for the delay. Okay, this talk is about data-oriented design for people who are not experienced in data-oriented design. I think a lot of us have seen videos about data-oriented design and thought it to be maybe a bit intimidating. Most of us know object-oriented design. The goal of this talk is to show you that this is another paradigm. It's not very scary. It's not the only thing you should use ever. But it's also the story of how I took a certain component and made it faster by a 40 factor. That is 40 times faster. So it is something, data-oriented design is something you should have in your tool set for those things that you want to have that much more faster. Now, before I go into what I did, I'd like to very quickly go about what's object-oriented design and what's data-oriented design. Object-oriented design, I assume most of you are familiar with it. There's a lot of definitions for it, so I'm not going to give an exact definition, and I'm going to give some very high-level things that will explain why people see object-oriented design and data-oriented design as almost polar opposites. So object-oriented design is about polymorphism. It's about objects that hide what they actually do from the programmer calling the object. It could be done using virtual tables, through message passing, through variants in C++, etc. The core of it, I'd say, is just, again, the question of you have an object, but you don't know necessarily what it does. You know what its signature does, but not what its internals do or how its internals are structured. Because it encapsulates all of its internals. And this encapsulation, I think, is very important because it's the concept, to me, it is the conceptual point of object-oriented design. The encapsulation is of all the properties relevant to the object. The examples we usually study are cars that have a wheel, that have 4 wheels and a chassis and 2 to 5 seats or more. And all of these properties are part of the car. A chair is defined as something that has 4 legs and a seat. And these 4 legs and the seat are all encapsulated within the chair. Essentially, it is everything that is the chair, that is relevant to the chair, is within the chair object. And this is where definitions become soft, but to me, they become very important because this makes object-oriented design very intuitive for people because we have, for several million years, seen actual physical objects, whether it is sticks, trees, stones, chairs, and cars. We see a car and we know in our mind to expand 4 wheels, chassis, 2 to 5 seats into this is a car. We have this intuitive understanding of what an object is. And when we structure our software, the way we think, the way we perceive the world, it is very easy to us to grasp our software. And essentially build the software as a way to mirror our internal worlds, and that makes it easy for us to understand what our software is supposed to do. And this ease makes it easier to maintain the software later on, or at least in theory it does. It means that we have a grasp of what it should do, and therefore how it should behave. On the other hand, object-oriented design, data-oriented design is about data. It is not about the several million years of us viewing real-life objects. It's about the roughly 70 years of us viewing bits and extrapolating data from it. Software is data manipulation. It's not about concepts. It's not about what should happen, but about what the computer actually does in practice. That is, transform one piece of data into another piece of data, whether it is in an internal calculation or it is in taking inputs and translating them into outputs on the screen. Both the inputs and the output are data. And once we view that, and then we say, okay, if we think about code, about what we do as a way to transform data, let's take out all the things which are slow, which slow us down. So when we talk, we need to think about what the computer actually does. We need to think about not do we have an abstract object, an abstract model, but about such questions about what do we put in memory? Where do we expect in the computer's varied levels of memories, where do we expect the computer to hold this particular piece of data? How much memory can we use? How much data can we handle at the same time? And how do we structure our software in order to maximally utilize this? This means that we do not want to grasp data, to bring data into memory by any way it should be used, but rather by what we use right now. If we talk about chairs in data-oriented design, we do not want, when we want to, let's say, recolor a chair's single leg, we don't want to bring into memory all 4 legs and the chair's seat, because 3 of the legs and the seat are completely irrelevant to the current transformation. And this might sound like not something which is that serious, but again, see the quote at the top of the screen. We're talking about 1,000,000 chairs at a time, then it's the difference between retrieving 1,000,000 legs and 4,000,000 legs and another 1,000,000 seats. Notice 80% of these 5,000,000 objects or 5,000,000 pieces of data are completely irrelevant. 4,000,000 bytes, let's say, of irrelevant information. They're not encapsulated by how we actually use the data. And I think the final crux of the thing is that there is no ideal solution. There is no abstract solution. Data is not abstract. Data is concrete bits sitting in concrete memory with concrete amounts of space that you can and should use. So you don't have a single solution which is good for all different computers, whether different sizes of memory, whether different capabilities of their processors, etc. You build your solution for the hardware that you write on. And I think that these two, yes?
I don't think it's necessary for the hardware running on because usually the hardware is pretty similar to any other hardware.
Okay.
But it's for the problem that you're facing because even say for a DB database that fetches stuff, there's a big difference between writing software that fetches a big amount of stuff contiguous between than using a lot of small
Eden, I'm sorry. Eden, I'm sorry because people who would listen to the microphone don't hear you. So in short, Eden said that it's not specifically the hardware, but the general problem space that you're tackling. And I think that the hardcore way to say it is that hardware is at least a part, if not most of the problem space that you're tackling. And in that it's correct. So I hope from the definitions I gave to you, it is pretty easy to understand that there is a clash between object-oriented design that wants abstract objects that match our psyches to data-oriented design that wants concrete data that works in the best possible way on the actual computers we run it. Now, what I want to say is it's not a matter of right or wrong. Some problems are problems that are easy. It's easier to tackle when we think about the data in terms of the computer. For example, performance problems are in the vast majority of cases, computer issues. That's the problem domains. Some things where it is an actual problem for us, for example, to ask, how do we build the software that solves this problem? That when we don't have the concrete transformation, it's a lot easier for us to understand what is the issue, what are the objects interacting in this scenario in order to model what do we want to do. So those are two different paradigms, and I'm not going to argue that one is better than the other. What I am going to argue is that one is significantly more performant than the other, and I want you to be able to make that mental switch between the two paradigms in order to use data-oriented design when you need it to. So what's the concrete case that we are handling here? I think this won't work. I tested it before, so let's quickly play the video here. Once I'll find the cursor. We're talking about video properties interpolation. You can see that the text moves across the screen, changes its opacity, and changes its color. Okay? Essentially, you have some things which are constant in the scene and some things which are which change between each scene. And for some reason, I have lost. Nope. Oh, it is a different screen of Chrome, but for some reason, Chrome doesn't. Oh, there we go. So essentially, some properties interpolate, some properties have different values at different frames, and some properties are constant throughout all of the frames. What's the model? What's the object-oriented model that I took at the beginning of the problem? Okay, so we have properties, a set of properties. We have a set of update operators, which define how these properties interpolate. How do we have the different values? We have a functor, an interpolator that knows how to interpolate a property based on time. I won't go into how the functor operates. Let's say it is an object that does a calculation. We have animations, which take a functor and a set of properties and know how to define essentially a single animation. And we have a single model. Now, a model in this case is a base class that contains certain properties, a mapping between each property and its update operator. This is the mapping. And animations. Now, you'll notice that the mapping is virtual because this is a base object. And concrete models will have different properties and different ways in which each property interpolates. For example, we saw in the video before two models in action. We saw a single text model, which has a string, which is constant, and locational scaling and coloring properties, which interpolate. And we saw in the background an image model, which has an image source, which is constant, and interpolatable properties of its location and scale and its opacity. How do we interpolate these values in an object-oriented way? Using a lot of internal loops. We have a vector of models. I'm sorry, as I mentioned, before I go into the code, this code is simplified C++. That is, I removed most of the qualifiers which make it hard to read the code. So if, for example, you notice something like this could have been passed by value or by reference or by pointer in order to make it faster, ignore it. Also, some of you might see some areas to suggest how the code could be better. We'll iterate through the code slowly. So come to me at the end of the talk if you think I missed something, because this is a system that we use, but don't at the middle of the talk, please interrupt with a suggestion because it might pop up by the end of the talk. So what do we want to do? Essentially, the object-oriented way is to have a collection of inputs of models. We have a certain point in time, and we want our output to be a different collection of models with their values interpolated from the model's base values and animations. So what do? We loop over all the models. For each model, we create a copy, and we get the model's update operators. And then for each animation defined in the model, we take the value of the specific interpolator, the interpolated value, and we combine it and set it in the copy. Okay? Then we push the copy into our vector, and once we finish iterating over every animation in every model, we just return the result of the operation. This is simple. It does, well, what it should do, but it does it relatively slowly. Now, in order to explain, by the way, is this clear? Because if you did not understand how this worked, you will not understand the rest of the talk. Clear, excellent. So in order to understand the first step I took in order to make this faster, there is a certain recurring concept in data-oriented design, which is called moving from an array of structs to a struct of array. We saw in the code before that we have a vector, which is essentially a contiguous memory array of the models. Notice that these are pointers in order to explain that these are inherited and not specifically structs of the type model, but some inheriting type. So we take the model and we break it down into its composing properties, and each one of the properties or types of properties we put in a separate array. So instead of having a single array where each cell in the array has an object of all the properties, we have multiple arrays, each one containing the properties relevant to a single operation, to a single computation. In that way, we can iterate over each array and do the operation of that certain array instead of retrieving all of the memory of all of the model for each computation. This breaks encapsulation. This is the first step in saying the model, the object no longer contains all of the information of the object. It is a way of breaking down the model into its component and what component is relevant for each computation. One moment. It allows better SIMD support for where it's relevant, because the less information you ask, the easier it is for the CPU to do it. And the complex part, or slightly complex part, is, if you've noticed, each model has a vector of animations. Now, if we'll take these animations out, we'll have a vector of vectors. What we do is flatten this down into a single vector of animations, and we just go, and each model knows to go into a certain portion of this vector. This concept is known as a span. Essentially, it's a limited sequence inside a collection. Think about having the full collection, the beginning of the sequence, and the length of the sequence in the collection. Once you have this span, it is very easy for you to say, these are all, for example, all the animations relevant to a certain model by having the span. Yes, there was a question.
Yeah, I don't believe it breaks encapsulation because...
Well, by definition, having an array of structs breaks encapsulation because you don't have a single object containing all of its properties. That is exactly what encapsulation means. You can have ECS system, entity component systems, which allow you to have indexes into each struct indicating where are the properties, but that's a system over this structure in order to simulate encapsulation. It is not the intuitive description of encapsulation that we have. There was another question? Yes.
So just continuing on the previous question, the encapsulation basically tells us that we don't show the world how the data is stored. So your record of it contains coordinates does not necessarily need to store it inside. I mean, you don't have to expose the record that stores
Okay.
that give access to the data. So just theoretically, you could store the index in an array inside the object, and all the access.
That's true. You could have encapsulation of data. Yes, I'll repeat it. What Yildena says is that you could have encapsulation by having an index into the array and having a method exposing this information. But that's not encapsulation, because you need to have the array of structs in order to get this data, and this array is shared between several objects. So we have several objects pointing at the same array, maybe using spans, but it's not, again, proper encapsulation because all the objects share the same data, share the same array. It's very similar to encapsulation, I agree with you. It's not very far from it, but it's not proper object-oriented encapsulation. So what values are we using now? We have a single animation, which again has an interpolator, but doesn't have the properties it animates over. We have a property which has a source value, the update operator, and by inversion of control, a span into an array of animations. And we have a model which has a span into the array of properties and a method that allows it to make another model of a certain type. Again, of inherited type. And this is the array of struct that allows us, that has the separate arrays. This seems a bit complex, and you'll see the code, and going over it very quickly, you'll see it is practically exactly the same code we saw beforehand, right? We iterate over all the models. Now we create a vector of the properties, iterate over the model's properties, again, extract their value, interpolate the value using all of the animations now in the property instead of it in the model, and create a copy at the end. Not such a significant change, except for one specific piece of information. And here we pre-calculated the update operator and moved it into memory. So essentially we have one less virtual call per model, but that's not such a significant change. What do we get here? Well, the ability to say we don't need the structure. We move this out, but we can also separate the model creation because we don't need the model in order to interpolate the values. Okay, so here we have an animation which has an interpolator index now, and we can separate. Here we interpolate over the values, but we have just arrays of properties, a single large vector of results, and we interpolate all of the results. And then after that, we go over the array of models. We take the relevant span, we create a span here into the array of results and make the model copy. Okay, we still have the same signature up to the changing input, but now we have separate two operations. Is this much better? Well, it's nicer to have smaller loops that do less. It means that the CPU needs to fetch less instructions and can operate quicker, but it means that this operation, this computation-intensive operation, does not allocate memory, which means that this part runs quicker. But the more important part of it is, okay, we have better memory cohesion because we drop the vector and we reduce the count of the virtual calls. The big change, though, is what we have now, which is the first half of that. We don't need to have model creation when we interpolate values. If you'll remember, when I told you at the beginning that data-oriented design is the question of how do you manipulate data, well, this is the data that you manipulate. This is the action of interpolation, right? The question of how do you later consume the data, whether you create models from it or just keep the spans and use a pair of non-interpolatable data, the strings, for example, with spans into the interpolated data, that's a choice that is left to the user. As far as the interpolation logic goes, we have very short operations, very succinct data, and this runs significantly faster. We can leave to the user the question of whether he wants to use it in a very efficient way or a less efficient way, which is more abstract to him. So no models, no dynamic allocation. We can pre-allocate the results. If you'll notice, now we receive, here I'm using the pointer to indicate that this is a parameter that is modified and can used externally. And the vector of results is modified. It's slightly more efficient. Again, we use spans into the vector of results, and you simply pair up a span with the model, which does not contain interpolated data. Again, all the constants, such as the strings, and you have smaller, non-encapsulated, smaller units, and simpler logic. Is this clear so far? Seems like it is. Great. Is this as good as it gets? Before that, yes, question.
Can you repeat again what are the models?
The models, okay, I'll move quite a bit backwards. The models are, for example, things like text, image, video. The models come from the object-oriented point of thinking about the whole thing, right? So what we did is separate. Now, at the result we've seen before, you would have a text model containing a string text, and it would still have this operation that gives you the map. But this operation would be used once when you construct the array of struct, instead of repeatedly throughout the interpolation process. But it will not have these interpolatable values. These will be held by the results object and the model. Again, when we move back to the pair, whoever consumes the model will be able to consume the interpolated values. We can still optimize it a bit more. We can say that calculating the results of the interpolation process is a separate operation from actually combining the values from the actual update value function. We can, as a first step, calculate all of the interpolations. And then instead of calculating it here, we can just access memory, and we can just access the memory from the result vector and get it faster here. Is this an optimization? Is this faster?
No.
Is this slower?
Yeah.
Okay, so we have one person saying this is slower, and the correct answer is it depends. If you have a lot of properties sharing the same interpolator, the same values in the interpolator, then you're doing the same computation over and over again, and it might be that memory access will be faster. In practice, as some of you have known since I pestered them about it, in the vast majority of cases, we have a single property interpolated with a single interpolator that is not repeated exactly to other properties in other models or in the same model, and therefore, yes, we're not only doing the same work here, we're also adding on top of that memory access, which, by the way, in some cases is significantly slower than actually computing a value. So this indeed is slower, at least for our use case. Let's have another optimization, a slimmer implementation, this time by just saying, what are we doing we are animating values. So instead of iterating over properties and then checking their animations, why don't we simply iterate over the animations? We have, okay, missed the pointer here. Again, we have the vector of results. We have all the initial values here. Let's only change values indicated that have been animated. If we have significantly less animations, then actual properties that we interpolate will do a lot less operations. Is this faster? Yes, no, maybe so?
Yes.
Eden says yes, even though Eden sat with me for the last 2 days trying to solve the question of why is this so much slower than the previous operation. This is so much slower. Why is it? This is about 40% slower than the previous implementation. Why is it slower? Because of these two actions. We have a read and a write from the same location. The compiler doesn't know that these read and writes are, that the next iteration will read and write from different places because it might not, right? One animation could read the result of a previous animation and iterate and write over it. So the compiler has very little room to optimize this code. The compiler doesn't know, and so it cannot unroll a loop. It cannot try to parallelize the operations, and it has very little room for maneuvering when you do that. So even though we have, let's say, a pure understanding of the operation here, when we actually look at the data and the actual operations that the computer does, we have much, much slower performance. Let's try it again. Yes, question.
Maybe it's a little bit off topic, and so to me. About the benchmarks, I mean, if you said before that it depends on several cases of things. So how did you decide, how did you test it? How did you say that this is 40%? I mean, I know that you compared the same data, but is it this data?
That's a very good question. So I had several benchmarks, and I ran them on my machine. The results could have been different on different machines. But yes, it's as simple as you run the benchmarks you have, you build benchmarks that you hope represent the common case, let's say like that. And if you have good benchmarks, then you had good performance data. And if you have bad benchmarks, then get good benchmarks.
So you use like benchmarks that you thought that is a common use?
Yes.
And took like several of those?
Yes.
And did like an average?
Okay, so let's try that again. What do we do here? It's much more complex, but not different by an idea. Now we take the index of results into a source value. We also keep the index as both of these are saved as variables, which means usually that the compiler will tell the CPU to save these values in a register and not write them over unless it needs to. And then we iterate on all the animations that share the same source index, that is, read and write to the same value as the first animation in this specific internal loop, and interpolate and update the value. And only after you finish going over all the animations that change a specific value, only then do you write it into the resulting array. Now, you'll notice here that this for loop, somewhat unconventionally, does not increment I. It is incremented in this do while loop.
That's fine.
Yes, exactly, and which is why I thought you would know. Is this faster?
It depends. If you change the source index every time, then it might
Okay.
be-
Ori says rightly, if the source index changes a lot, then we have the last case. And let's make it even worse. If you don't order your animations so that all the animations that change a certain value are and do come one after the other, then you will not get better performance. Also, the sad truth is that this isn't much faster. It's roughly along the performance of the last baseline. I would be very happy to explain to you why, if I would have known. Whoever can tell me why this does not perform much better than what, we'll get a burger or the equivalent meal. We have some ideas, again, of why the last thing worked and why this works now. That's, as I said, the general things. So going back to the ideal solution, what would be the ideal solution? And the answer is not what I showed you before. Why is that? Because, as I said before, we're not going into the interpolator implementation. We have several interpolation functions, and that's polymorphism. We have several update operators. That means you have, when you update a value, you use an if or switch statement in order to decide what is actually done. We would have had much better performance if we would have split the table of operations into several tables, each one for a certain update operator, a certain update operator and a certain interpolator, and then the core loop here, no, sorry, the core loop here would have done exactly the same thing for each animation in each table. We would just run this logic several times in order to cover each separate interpolator and a combination of each separate interpolator and each separate update operator. And then at the end of that, we'd need to be able, first of all, to split our data before the operation once, again, as a pre-processing step, in order to have separate operations, each one doing exactly the same thing, several tables, each one representing exactly the same calculation, and then after the interpolation, combining all the results back to the shape of the data that is consumed later on by the video rendering engine. And that would have been that much better because the compiler, the processor, will do exactly the same thing, step after step. And as I said, sometimes instruction fetching, sometimes branch prediction is what makes your code slower. And when I say sometimes, some people would say almost always it is what makes your code slower. So why didn't I do that? Because sometimes you need to actually finish your code reviews and have your code submitted. And going back to the beginning of the talk, I want to have these things. I could have done all of that, and it would have taken that much more time to do and check and verify. And sometimes you do try to optimize for several things, not only performance, but also programmer time and efficient usage of your time just to develop all the rest of the things. So it's not always about having the most efficient code. The code I showed you is fast enough. It can render 60 frames a second on a relatively weak machine. It could have been faster. Maybe when I'll have the time, it will be faster. But for the while, just having the idea of how I can take step after incremental step in order to make that code faster is good enough for me. And I hope that what you take from the talk is that it's also good enough for you. Just once you break out of the object-oriented mindset, you can use data-oriented mindset in small steps. You don't have to see, those somewhat intimidating videos of people talking to you about the size of cache lines and what's the performance of certain CPU instructions, and say, I am unable to do that. I don't have the knowledge. Just do things one step at a time and get your code that much faster. Question? Yes.
About the most recent solution you talked about, the interpolator, does what it does change as a result of like tangents and stuff, like easings, and if so, does it add additional cost of like branching once it does it?
So the interpolator in practice is it's a base class. It's a base functor to be exact, and it has several implementation. So you have different types of interpolator. You have a linear interpolator, a sinus-based interpolator, etc. So the actual calculation that is done is different from animation to animation, which means that yes, you are losing performance just in getting, you know, the specific instructions run by this certain animation. Does that answer your question? Yes. Something else? Yes.
No, are you done?
I think so, yes.
Are we going to questions?
Yeah.
Right, so Nimrod asked to finish like 5 to 10 minutes before so people can get to the Q&A if they want to. So I guess you'll stay for questions if you want to take it offline.
Sure.
Thank you very much.
You're welcome.